This is CX1104 Linear Algebra for Computing, Chapter 6.2.4. In this chapter, we'll talk about octonormal sets and orthogonal matrices. What is an octonormal set? An octonormal set is a set of vectors that are not only orthogonal, they also have unit length factor 1. So they are described by two terms, octo as in part of octagonal, and normal as a normalized vector with unit length 1. If W is a subspace spanned by such a set, then this set of vector is called the octonormal basis. Remember, a basis is a set of vectors that spans a space. So U1 to UP spans a space W. If U1 to UP is not only orthogonal but octonormal, they are an octonormal basis. The most common example, simplest example of an octonormal basis is the standard basis, where E is 1, 0, 0, and then, for example, the last one is 0, 0, 1 for the R3 standard basis, and E2 is of course 0, 1, 0. In this example, we are shown V1, V2, and V3 that are orthogonal to each other. Now, therefore, because they are orthogonal to each other, they form an orthogonal set spanning the R3 space. If V1, V2, and V3, the length is also equals to 1, then V1, V2, and V3 is an octonormal set for R3. An example of this, V1, V2, V3 is here. V1, V2, V3, first we want to prove that they're an octonormal basis. We have to first prove that they're orthogonal first by computing the dot product between V1 to V2, V1 to V3, and V2 to V3. That means all possible pairs. If the results are 0, they are orthogonal, then we can now find whether they are octonormal. The length of V1 is equals to V1 dot V1 square root. In this example, V1 dot V1 is equals to 1. Square root of 1 is 1, so the length is 1. Same with V2, V3, and therefore V1, V2, V3 is an octonormal set spanning R3. Therefore, they are an octonormal basis for R3. So this is the example here. Now in MATLAB, I can very quickly check whether V1, V2, V3 is orthogonal or not by doing this. We simply have a matrix, and let's call it S3, transpose S3. Right? Therefore, what we are doing is that we are taking the column vectors, we're transposing, so we are making the first vector as V1 transpose, and we are taking the other one as V1. So we are computing the V1 transpose V1 here. Here is V2 transpose V2 here. This is V3 transpose V3 here. And then this is V1 transpose V2. The other guy is V1 transpose V3. So very quickly, by performing it on a matrix multiplication of S3 transpose S3, when we get an identity matrix, then this shows that these three vectors are octonormal to each other. They are both orthogonal, their length is 1. Let's see octonormal sets again in the form of U transpose U. If a matrix U, it can be rectangle, it has octonormal column, then we can very quickly know that it has octonormal column by performing U transpose U. Why? What is U transpose U? Well, let us now have three octonormal columns in this example, U1, U2, U3. When we perform U transpose, therefore we are getting it as now row vector. So U1 transpose, U2 transpose, U3 transpose. We are multiplying U transpose with U, so this is the column vectors of U. The entries are U1 transpose U1 in the diagonal, U2 transpose U2, U3 transpose U3. This will show us the length squared. Now we need the length squared to be 1 because we need the length to be 1. Therefore, along the diagonal, we'll get identity. Now, what about all the other terms? All the other terms should be 0 because if the column vectors are orthogonal, then the dot product of U2 to U1, U3 to U1 will be 0. Now, so we show an example when U is a square matrix, that means 3 by 3. So these are the 3 columns of U, U1, U2, U3. Very quickly we compute U transpose U and we get the identity. So this shows that the columns are octonormal. Now what about U transpose? So U is 3 by 3. U transpose is also 3 by 3. We also get the identity. In this very special case, then the matrix U is called an orthogonal matrix. Okay, it has a very special name. When its inverse is equals to the transpose, and then we can get U transpose U and U transpose to be identity, then this is an orthogonal matrix. Now, what about when U is rectangle? So we now only take 2 columns of U from the previous example. So this is U1, same as this guy here. This is U2, same as this guy here. Therefore, from the previous example, we know that these columns are not only orthogonal, they are octonormal. Let us compute U2 transpose U2. The 2 here stands for the 2 columns of U. We get identity because remember, although U3 is 3 by 2 matrix, U2 transpose is a 2 by 3 matrix. U2 is a 3 by 2 matrix. Therefore, what we get is a 2 by 2 identity. Now, what about U2 transpose? U2 is a 3 by 2 matrix. U2 transpose is a 2 by 3 matrix. We get a 3 by 3 matrix. So although we get a 3 by 3 matrix, it is not the identity as in the last example. The last example, we got an identity, but here we don't get an identity. This is a very special matrix. Let's call this matrix P. Okay, P is U2 times U2 transpose. This is this guy. This matrix has only 2 independent rows or 2 independent columns. How do we know? We compute its rank. The rank of P is 2. Not only that, P times P is equals to P. So this is P, this is P times P, and if you compare the entries, they are the same. In another lecture, I'll explain that any matrix that satisfies P equals to P squared is called a projection matrix. So in summary, if I have a matrix U and it is number of rows is m and the number of columns is 2, for example, then this matrix, let's say these two columns of U are octonormal. Then we want to ask the generic question, what are the characteristics of the matrices for U transpose U and U transpose? First is U transpose U will give identity because the two columns are octonormal. This guy will not be identity. First, it will be dimension m by n, m by m. This is a square matrix, but it's not identity. It has a rank of 2 because it only has 2 independent columns. It was formed by 2 independent columns. This P matrix spans the column space of U, and later on we will show that it is called a projection matrix because P equals to P times P, and the P matrix can be used to project a given vector Y. So by U transpose to project Y into the space of U. Okay, so P times Y will give us Y hat, which is the best approximation of Y in the column space of U. You can see this in chapter 6.2.5.